today we're going to start discussing something else. I mean, last day, remember, we obtained the Euler-Lagrange equations of motion, starting from D'Alembert's principle and the concept of virtual displacements. Now, we're going to start discussing what is called most books call it the least action principle. So it's an action principle, but actually it's not the least of anything, is actually the stationary. Is the stationary action principle. So we'll have to define what an action is and what is this principle that makes the action stationary. By stationary, what I mean is that there's going to be something that is the action that we are going to look for an extremum of it. And this extremum, we are not going to care whether it is a minimum or a maximum or a saddle point. We just want the action to be stationary, so that the action is going to be constant under variations of something, okay? Some books call this thing least, but it's not true, because sometimes the action, what we're looking for is not really, a minimum of the action. It could be a maximum or a saddle point. So we will stick to this stationary, action principle. And before we get to that, which is physics, we're going to do a little introduction to what is called calculus of variations, which is the mathematical language that we need to study this stationary action principle. So what does the calculus of variations study? So the calculus of variations studies and looks for the particular path y of x, so that's going to be a function, between two values x1 and x2, which makes the line integral j equals integral dx from x1 to x2 of a certain function f, y of x, y dot of x, and x is stationary. Okay, so let's see what we have here. Okay, so this j is a line integral, is the integral of a function which depends on the function y of x, derivatives of the function y of x. So by y dot of x, what I mean is the derivative of y with respect to x, so that's not anything strange. And what we have to realize is that this line integral j is actually not just a function, but a function of functions, right? It depends for each function y and each derivative of y. We just stick it in here. This f is going to be some expression, and then we integrate over x from x1 to x2. So this whole integral, this whole line integral, is actually something that depends on the function y, the derivative of the function y, okay? So it's not just a function, but a function of functions. So a function of functions is what is called a functional. Is a function of functions. So the situation is that we have x, we have x1 and x2. At x1, we have a value y of x1. At x2, we have a value y of x2. And we want to know between these 2 points, x1, y of x1, and x2, y of x2, which is the function y of x, that makes j stationary. So there will be one function y of x such that when I put it in here and I do this integral, little variations, like for instance this one or that one or this one, okay, little variations with respect to this value, this function y of x, make j like acting like a constant. It does not change. So that's what what I mean by stationary. Okay, so that is the thing that we want. Okay, so this, for instance, this function here is going to be a function that starts at the solution, so this is the solution which makes J stationary, and then I vary this solution with an arbitrary function eta of x. Okay, so this is a variation. It's clear that if y of x0 is precisely this y, so this is y of x, the one that is making J stationary, and that's the solution I'm looking for. When I make a variation with respect to this solution, then I get to all these different orbits, all these different functions, y of x, and the condition on this arbitrary function, y of x, has to be that at both x1 and at x2 vanishes. It has to vanish because necessarily, even though I am varying from y of x, it has to go, you know, through these 2 points, right? Through the initial point and through the final point. So this variation has to vanish at both ends, okay? Now, if I replace this variation inside the line integral, then, and I use this alpha as the parameter, then this functional here, the functional integral that I have here, becomes just a function of alpha. So now I have my functional is just a function of one parameter alpha, which is the integral from x1 to x2 of this function f y of x and alpha, y dot of x and alpha and x. And now J of alpha stationary is the same as derivative of J with respect to alpha equals 0, of course. I repeat that, you know, this could mean that, you know, we find a minimum, we find a maximum, or we find a saddle point. We don't care. What we care is that it is stationary. So the variations are, you know, make the derivative vanish. Now, let us see what happens if we impose this condition on this functional, okay? Well, we have to take the derivative of J with respect to alpha, and this is, of course, the derivative with respect to alpha of this integral from x1 to x2 of this function y of x and alpha, y dot of x and alpha, and x. And remember that y of x and alpha is y of x0 plus alpha eta of x, with the boundary conditions eta x1, eta x2 equals 0. Okay? So let's take this derivative. So what is this derivative? So this is integral dx from x1 to x2. And this is partial of f with respect to y, partial of y with respect to alpha. That's one term, right? It's the variation, you know, of this whole thing with alpha through y, okay? So that's one term. But there is another term because y dot also depends on alpha. So this is the derivative of f with respect to y dot, derivative of y dot with respect to alpha. And that's the end of the story, okay? So now, let us look at the second term. So this second term here, okay? So this is the integral over x from x1 to x2 of the derivative of f with respect to y dot, derivative of y dot with respect to alpha, okay? Now, if y of x and alpha is given by y of x0 plus alpha eta of x, then what is y dot? Well, y dot of x and alpha is the derivative of this thing with respect to x. So that is y dot of x0 plus alpha eta dot of x, because alpha does not depend on x. So if I take the derivative of this whole equation, what I get is this, okay? So that means that this is the integral over x from x1 to x2, partial of f with respect to y dot, and this is the derivative with respect to alpha of the derivative of y with respect to x, okay? But the derivative of y with respect to x, derivative with respect to alpha, they commute because alpha does not depend on x. So this I can also write as the integral dx from x1 to x2, partial of f with respect to y dot, derivative with respect to x of the derivative of y with respect to alpha. Okay? Good. Now, I can take this derivative with respect to x and integrate by parts. So this is going to be integral dx from x1 to x2. And now I write this as the total derivative with respect to x of the whole thing, which is partial of f with respect to y dot, partial of y with respect to alpha, minus the other term, which is the derivative with respect to x of the derivative of f with respect to y dot, times derivative of y with respect to alpha, right? Because in this derivative, I have this derivative of f with respect to y dot, which I cancel with this one, and then I have derivative of f with respect to y dot times the derivative with respect to x of the derivative of y with respect to alpha, which is exactly the same thing as what I have here, okay? Because now this only depends on x. Good. So what is this thing? Of course, the derivative of y with respect to alpha, derivative of y with respect to alpha is nothing but the derivative of y with respect to alpha here is nothing but eta of x, right? So this is the same. Since here I have the integral of the total derivative, this is nothing but the derivative of f with respect to y dot, derivative of y with respect to alpha, which is eta of x, evaluated between x1 and x2, minus the integral dx from x1 to x2, now the second term, the derivative with respect to x of the derivative of f with respect to y dot, derivative of y with respect to alpha. Okay? But what the boundary conditions tell me is that this term here, both at x1 and x2, vanish because the function eta of x, vanishes at x1 and x2. So this term is actually not there. So that means that my derivative of j with respect to alpha, so I'm reading again this expression here, is the integral over x from x1 to x2, the derivative of f with respect to y, derivative of y with respect to alpha, plus this other term, which I just computed, which is minus derivative with respect to x of the derivative of f with respect to y dot, derivative of y with respect to alpha. And so that means that I can factor out this term. I'm going to factor it out. So that means it's integral dx from x1 to x2. And now partial of f with respect to y minus derivative with respect to x, partial of f with respect to y dot, this whole thing times derivative of y with respect to alpha. Okay? So any questions or comments about these manipulations?
No.
Yes, please. Just a silly thing. When you changed in this thing you are marking right now, you changed in the la part de baix, en el denominador, the x and the alpha. When can you do that and when you cannot?
You mean why is it that I can go from here to here?
Yes, exactly.
Well, I mean, look at what y is. Y is this expression, right? Y is this thing here.
Yes.
Okay, so if I take the derivative with respect to x first, and look at this part, I'm going to have alpha times eta dot.
Yeah.
And if I take the derivative with respect to alpha, then I have eta dot. Okay?
Yes.
Now let's do the other thing. Let me take the derivative with respect to alpha first. Then I get eta of x.
Okay. Yeah.
And now let me take the derivative with respect to x. I get eta dot. So it's obvious that it is the same. And the reason why it is the same is because alpha does not depend on x.
Okay. Okay, okay. Fine.
Any other question?
No, thank you.
Okay, so now let us look at this expression that we just found, okay, which says that the derivative of j with respect to alpha is integral dx from x1 to x2. And here it said derivative of f with respect to y minus the derivative with respect to x, derivative of f with respect to y dot. And then it said derivative of y with respect to alpha. But what is the derivative of y with respect to alpha? Is eta of x, right? Is this arbitrary function? Eta of x is an arbitrary function except for the boundary conditions. So I'm going to repeat the boundary conditions. Okay? And notice nothing, I'm going to say it explicitly, nothing is said about the derivatives at the boundary conditions. So they are free. The conditions are only the conditions are only on the function, not on the derivative. Okay. Now there is a lemma of the calculus of variations, which I'm not going to prove. Okay, that says that the integral from x1 to x2 of a certain function of x, eta of x dx equals 0 for all eta of x sufficiently well behaved. That usually means infinitely differentiable. So if this integral for all eta of x infinitely differentiable vanishes, then m of x equals 0 in the interval x1, x2. Okay? So if this is true for any eta of x infinitely differentiable, then the integrand vanishes. Not just the integral, but the integrand. Okay? Now, let's apply this lemma to our case, because what does stationarity mean? Stationarity now means that this derivative of j with respect to alpha vanishes. But this is nothing but the integral over x from x1 to x2 of this integrand times precisely one of these functions. So this means that as a consequence of the lemma, now the integrand vanishes. Okay? So this is, in mathematics, is called Euler's equation. And in physics, we also call it Euler's and Lagrange equation. Okay? So now, of course, we're going to see that this has, a clear application in physics, right? Because if I defined, this little f as the Lagrangian, what I'm going to have here is nothing but the Euler-Lagrange equations, as we derived them, last week from D'Alembert's principle. Okay, so this is why this thing is now very interesting. We have another way of deriving this equation, which comes from an action principle, and this has certain advantages that we are going to emphasize. Okay, so a typical example that you can work out is find the shortest distance between 2 points in a plane. So that means I have x1 and x2. This is y of x1. This is y of x2. And now the question is, which is the path that connects these 2 points, y of x, such that the distance is a minimum? In this case, we know it's a minimum. It's not a maximum, and it's not a saddle point. And we also know the answer. Okay, the answer is a straight line. The answer is the straight line that connects these 2 points. This is obvious. We know that the answer has to be this thing. But now the exercise is show it. Show this. So write, what is the distance between these 2 points for any path connecting them. Okay? Apply Euler equation and find that indeed, the solution is a straight line. So is the exercise clear?
Yeah.
Yes.
And it's also simple. It's very simple. Okay, so now is when it comes the application of this calculus of variations to physics. And this goes by the name of Hamilton's principle. So Hamilton's principle is actually a principle that will derive Lagrange's equations, okay? So imagine that we think of what is called the configuration space. Configuration space. Configuration space is the space of all the generalized coordinates, Q1, Q2, and as many as you have, and time, okay? So I cannot draw more, okay? I can only draw 3 axes here. So therefore, Q1, Q2, and time. And then the solution to the equations of motion is going to be a path that connects these 2 points, right? This is going to be a trajectory, right? So this is going to be a trajectory in configuration space, clearly, right? Because the solution to the equations of motion is going to be a collection Q1 of t, Q2 of t, all the generalized coordinates as a function of t, and that describes a trajectory in this space. Okay, so this is the definition of configuration space. Okay, good. Now, what is Hamilton's principle? Hamilton's principle says the motion of the system from T1 to T2 is such that the line integral, which we will call the action or the action integral, defined by, and we call it S, integral dt from T1 to T2 of the Lagrangian, which is a function of q of t, q dot of t, and t, as many q's as we have in our problem. Doesn't have to be only one, where L equals t minus b is the Lagrangian. So this S is stationary. Maybe I should say is stationary for the actual path of motion. That is to say, for the solution to the equations of motion. Okay, so that's Hamilton's principle. So what Hamilton is saying is, if you want to know the solution to the motion of a certain system that goes from T1 to T2, write down the action, which is the integral with respect to time of the Lagrangian, and impose this stationarity condition that we looked at, that we studied, in the previous slide. Okay, so now note that in order to write down, an action, we need a Lagrangian. So the system has to have a certain Lagrangian L, which means that if the system has generalized forces which do not derive from a generalized potential, then we don't have a Lagrangian, and in this case, this action principle would not work. Okay, so for the action principle to work, we need a definite Lagrangian. The system has to be described by a Lagrangian. So let's see what this tells us. Okay, so now the situation is that, let's imagine that we have only one variable q. So we're going from T1 to T2. At T1, the system is in position QT1, and at T2, the system is in position QT2. And now we want to know which is the path Q of t, which makes S stationary. Okay? So, of course, what we're going to do, we're going to take, Q of t as we're going to vary it exactly as we did before in the calculus of variations, right? So we're going to take a q of t varied by a certain parameter alpha, which is going to be q of t0 plus alpha times eta of t. Sorry, not x. T. Now is t. With the boundary conditions that eta of t1 equals eta of t2 equals 0, and no condition on the derivatives at t1 or t2. Okay, so the derivatives are totally free, but the function itself has to vanish at both ends. Okay, so now s again becomes a function of alpha. This is going to be the integral over t from t1 to t2 of the Lagrangian q of t alpha, q dot of t alpha, and t. Okay? Now, notice one thing. When I take variations of q with respect to alpha, I take the derivative of q of t alpha with respect to alpha, and of course, as I did before in the calculus of variations, and this is eta of t, notice that I'm taking a variation of q with respect to a parameter alpha, and that is at fixed time. So the time here is fixed. These variations that I'm taking by going to different paths like this one, that one, or this one are variations with respect to alpha. T is fixed. So if you remember, what was a variation of the generalized coordinates keeping time fixed? That was nothing else but a virtual displacement. So a virtual displacement, so let me just write now here something so that delta alpha equals delta alpha. Okay, and this is a time fixed. So let me write it here. So this is delta alpha, and this is t fixed. So it turns out that these variations that we are taking, these varying paths that I'm considering in order to find which is the path that makes the action stationary, are variations that I'm taking at time fixed, right? The time is fixed. So that means that it coincides with what we discussed, last week, and how we define the virtual displacement. So now this delta Q coincides with a virtual displacement. And this will be interesting in things that, will follow. At this point, I could have avoided, mentioning this thing because it doesn't matter. I mean, now I'm going to apply this thing and I'm going to apply the calculus of variations the same way. And I'm going to get, the answer that you guys can already expect. But I want to mention that these variations here, the variations that we're taking with respect to this parameter alpha, actually coincide with what we define as the virtual displacement because they are taken at fixed time, okay? Okay, so now, if we take this action, this functional here, and we take these variations, I'm not going to repeat the same thing that we have just done, for the calculus of variations. It's obvious that what we're going to get is that the derivative of s with respect to alpha equals 0 is nothing but the integral over t from t1 to t2 of the derivative of L with respect to q minus the derivative with respect to t of the derivative of L with respect to q dot delta q for 1. And if we have more than one generalized coordinates, then I have an I, an I, and an I, and then I have to sum over I from 1 to n. Okay? Now, this means, according to the lemma that we already stated before, that the sum from I equals 1 up to little n of the derivative of L with respect to qi minus the derivative with respect to t of the derivative of L with respect to q dot j, q dot I, delta qi is 0. So now it's the integrand which is 0. Now, there is an extra step that I can take because the delta qi's are the generalized coordinates. So therefore, they are independent. They are independent from each other. That's a property of the generalized coordinates, right? These virtual displacements are completely independent from each other because the generalized coordinates, remember, have already solved the constraints. So now they can freely move independently from each other. And this means that it's not the whole sum that is zero, but each of the summands is zero. So it's partial of L respect to Qi minus d dt partial of L respect to Q dot I. Now this is zero for all of them from 1 up to little n. And these are indeed Euler-Lagrange's equations of motion. So now we have derived Euler-Lagrange equations of motion.
Paris,
Yes, from an action principle. Yes, questions?
Yeah, sorry, just a silly thing. In the first integral, well, I think we skip the function, the arbitrary function, right? Or
no, because let's go back. What is delta Q? Is precisely the arbitrary function. So here I could also write this thing as eta I of t, eta I of t, and they are all arbitrary, but at the same time independent from each other, right? Look at this. Look at this expression. The variation of each Q, which is a virtual displacement, is this arbitrary function. So then I would have here one arbitrary function for each generalized coordinate, this is Qi. Okay, so therefore the whole sum is zero, but these virtual displacements are completely independent from each other. So therefore this is true for each and every one of them. Okay?
Yeah.
Any other question or comment?
Yep, I have one more question. Because all of this, what we just derived, is like we take from Hamilton's principle.
Yes.
Is it possible in somehow to justify Hamilton's principle on the ground of classical mechanics?
Well, it's a principle. That means that you have to take it as it is. And it leads to some equations that you have also derived in another way, right? A principle is not a theorem, but you can show that if the system obeys these equations, it also obeys Hamilton's principle, and if it obeys Hamilton's principle, it also obeys these equations. I mean, the connection is one-to-one, but it's a principle.
Okay, so I could show this like going back from the list.
Yeah. I mean, if this is true, right? If this equation is true for each variable, you can work your way back. Yes.
Okay.
But it's also true that, you know, Hamilton's principle is a principle, because what would you do if your system has generalized forces which do not derive from a Lagrangian? You could still write down Euler-Lagrange equations of motion. Remember, then you would have here a Q tilde, right? Here on the right-hand side.
Yeah.
But you wouldn't know what to do with the action because there is no Lagrangian. So you see, in general, they are not completely equivalent.
Okay.
If you have generalized forces which do not derive from a Lagrangian, then the system is not fully described by a Lagrangian, and therefore you cannot start. This first thing that we wrote down, it doesn't exist.
Yeah.
So Hamilton's principle is equivalent to Lagrange's equations when the system is fully described by a Lagrangian. Okay?
Okay. Thank you.
I have a question also.
Yeah?
What I understood that Bartek was trying to say is that, okay, so they're equivalent and Hamilton's principle is a principle, but I mean, what I understood is there any physical intuition that would lead someone to think that such a principle as Hamilton's would be, I don't know, like physically plausible to describe the motion of a system? I mean, how could you come up with such a principle without knowing that it will lead you to Euler-Lagrange's equation?
Yeah. Okay. So in other words, what was Hamilton thinking when he proposed his principle?
That's the question. Yes.
I don't know what he was thinking. And I would say that probably he was thinking about something that it would be completely unexpected for us. All I can say is that these things do not happen, on a blue Monday, when you wake up and the best thing that comes to your mind is, okay, so let's take, this stationarity principle as my principle. These things do not happen like this. What happened is that, people were working with, D'Alembert's principle, and they were finding these equations. And then parallel to this, mathematicians were thinking about problems that had to do with this stationarity principle. And there was a famous problem for the mathematicians, which is the problem of the brachistochrona. Okay, so this is a terrible name. Mathematicians wanted to know which is the curve between 2 points that minimizes the time that it takes, under free fall. This is called the brachistochrona. Let's see whether I can write it. Brachistochrona, I think. Okay, is the curve which minimizes time between 2 points in free fall. Okay, so they were thinking about this problem. So this comes, by taking the you have to minimize a line integral. It's not the action, but you have to minimize a line integral. And it so happens that they had to develop the calculus of variation for this problem, and they came up with equations that look very much like Lagrange's equations, and so they made the connection. Okay. So what I'm saying is that it's not obvious at all that you would start by imposing this stationarity principle, and that immediately Hamilton saw that this was going to lead to Lagrange's equation. He was helped by other problems, and by the coincidence, if you wish, that the solution to this brachistochrona problem is actually Lagrange's equations. So it made a connection between two different things.
Okay, thank you.
Okay. So now we need to discuss the advantages of this formulation. What is the advantage of thinking, in terms of an action principle? Do we get anything for free? Is it better for some things? And it is better for some things. But it's already, 6:50, so that we have to leave it at this point. So we'll take over tomorrow. Tomorrow we have a class at 2:20. Okay, so we're gonna stop right here, and we'll resume the discussion of the advantages tomorrow at 2:20. Okay.
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 All right. So I'll see you guys tomorrow.